Hello everyone. I am Dr. Krishna Sarker, Department of Electrical Engineering. Here in this session, I will be going to discuss about controllability test. This is state space analysis, control systems, lecture series on state space analysis, lecture number 35. Overview, state variable formulation. What is controllability? Kalman test for controllability. Proof of controllability. What is controllability matrix? Theorems on controllability. Idea of complete state controllability. This is our overview. So Kalman test for controllability. The state variable formulation of an nth order linear time invariant multivariable system represented by the vector matrix differential equation. Consider the dynamical system described by the state equations are x dot t equals to xt plus but and yt equals to cxt plus dut. So x dot t equals to xt plus but. This is the state equations. Why state equation? Because left hand side, this is the left hand side, left hand side differentiation terms only, and right hand side free of differentiation terms. This type of equation is called state equations. So this is the state equations, and output equation yt equals to cx plus du, where when d equals to 0, that means this time this is equals to 0, then the output equation is yt equals to c into x. So these two equation actually MIMO system, MIMO, multi-input, multi-output systems. When d equals to 0, then state equation equals to x dot t equals to axt plus but, and output equals to yt equals to cxt. And this is the SISO system, that means single input, single output system. Controllability. What is the definition? This is the definition 1. The state equation 1, that means x dot t equals to xt plus b ut and y equals to yt equals to or y equals to cx plus du, or the pair of AB is said to be completely state controllable or simply controllable if for any initial state x of 0 and any final state x of tf there exists an input sequence which transfer x0 to xtf. For some finite t, otherwise the state equation is uncontrollable. So what is the equation? Equation equals to x dot equals to ax plus bu, and a is a constant matrix, b another constant matrix. So controllability test depends these two coefficients a and b, and initial time x of t0, and that means t0, and final time tf. What is the definition 2? Complete output controllability. This is the complete output controllability. The system given in equation 1 is said to be completely output controllable or simple output controllable if any final output can be reached from any initial state x of 0 by applying an unconstant input sequence u of t for some finite t. Otherwise, equation 1 is not output controllable. So this is the equation, this is the definition 2, and this is definition 1. And another definition, this is definition 3. What is the definition, controllability definition? A system is said to be state controllable at t equals to t0 if it is possible to transfer the initial state x of t0. So this is the initial state x of t0 to any final state x of tf. So initial state x of t0 and final state x of tf in finite time using an unconstant control signal u of t. If every state is controllable, the system is said to be completely state controllable. Complete state controllability or simply controllability, if no other context is given, describes the ability of an external input to move the internal state of a system from any initial state to any final state. Initial state means x of 0 and final state x of tf. So final state in finite time interval. So this is the definition 3. This is the definition 3. Concept of controllability. What is the concept? Consider the general structure of a control system as shown in figure below. This is the figure where input, this side input, plant input mainly, and this is the x dot t equals to xt plus but and yt equals to cxt plus dut. This is state equation and yt equals to output equation, and this is the output. This is the output and this is the state. And input equals to maybe step, ramp, parabolic, impulse, any type of input you can apply. There are two basic questions that we come across while controlling the system. This is the condition 1. It is possible to transfer any state x of t0 to any other desired state x of tf in a finite time interval tf minus t0 under the effect of a suitable input u of t. So initial state, this is the initial state x of t0 and another state, final state x of tf. And what is the time interval? Tf minus t0. So this is the initial state, this is the final state, and the time interval tf minus t0 under the effect of suitable input u of t. And second condition, this is the second condition, is the possible to determine initial state of the system by observing the output t0 to tf and input u of t0 tf over a finite time interval tf minus t0. This is the output y. This is t0 to tf. That means t0 and final time tf. This is the output y. And similarly, u input u of t0 comma tf over a finite time interval tf minus t0. This is the condition 2. Kalman test for controllability. A system is completely controllable if and only if the rank of the controllability matrix Q is n, where Q is defined as this. What is the Q? Q equals to B, AB, A square B, A cube B, dot, 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 A n minus 1 whole in A to the power n minus 1 into B. And this is the n cross n matrix. If n cross n matrix, then rank equals to n. If rank equals to n, then system is controllable, otherwise uncontrollable. This is the condition. So controllability matrix Q equals to BAB, A square B, A cube B, dot, 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 A to the power n minus 1 B. A system is said to be completely state controllable if it is possible to find an input u of t that will transfer the system from any given initial state x of t0 to a given final state x of tf equals to 0 over a specified interval to time tf minus t0. So initial time t0 and initial state x of t 0. Similarly, final time t of tf and final state x of tf and input u of t. So condition, this is the controllable when q0 rank equals to n. In the controllability matrix q0, since the matrix A and B are involved, sometimes it is said that the pair AB is controllable, which implies that the controllability matrix Q0 is of rank n. Again, when Q0 rank is n, the system will be controllable. Otherwise, uncontrollable. If the rank of Q0 is not n, then the system is not controllable or is said to be uncontrollable. This is the very important sentence. Proof. So Kalman test, proof, and controllability test, proof. Consider the state variable model of a system given in equation 1 and 2. The dynamics of a linear time invariant system be written in vector matrix differential equation is as. What is the vector matrix differential equation? X dot equals to x plus bu, y equals to cx plus du, or x dot equals to axt plus but and yt equals to cxt plus dut. This is the vector matrix differential equation. What is A, B, C, and D? Where A is a constant matrix or system matrix of order n cross n. This is the very important A matrix dimension n cross n. And B is the input coupling matrix of order n cross r. And U is a r cross 1 input matrix. And x dot equals to x plus bu is called the state equation. So this is the state equation. Again, yt equals to what? Yt equals to output, and this is equals to cxt plus du of t. And where y is a m cross 1 output vector, and C is m cross n system matrix, D is a m cross r transmission matrix. This is the transmission parameter, transmission matrix, and yt equals to cx plus du ut is called the output equation. So this is the state equation and this is output equation. So x dot equals to x plus bu. X dot equals to x plus bu. Just x right hand side to left hand side transfer, and we get x dot t minus axt equals to bu of t. This is equation number 3. Then multiplying both sides by e to the power minus at, and we get multiplying both sides by e to the power minus at, and we get e to the power minus at. This is the e to the power minus at, and multiplying both sides. This is the left hand side term and this is right hand side terms. So multiplying both sides, and we get x e to the power minus at, x dot t minus axt equals to e to the power minus at bu of t. This is equation number 4, and this is equivalent to left hand side equivalent to what? Left hand side equivalent to ddt of, this is equivalent to ddt of e to the power minus at into xt, because if this is u and this is v, first this term constant, this is constant, and second term derivative x dot t, and then second term constant, first term derivative e to the power minus at into a. So a into e to the power minus at. This is the definition, UV differentiation. Then right hand side e to the power minus at, x dot t minus a into e to the power at. This is equivalent to actually this term equivalent to left hand side. This is equivalent to left hand side. Then ddt of e to the power minus at, xt equals to e to the power minus at common, x dot t minus axt. This is the equation number 5. This is the equation number 5. Then equation 4 and 5. From 4 and equation 5, we get left hand side ddt of e to the power minus at xt, ddt of e to the power minus at into x of t, and right hand side e to the power at minus at b into u of t. So this is the equation number 6, and this is the very important equation. This is the very important equation. Then integrating both sides of equation 6 between lower limit 0 to upper limit t, and we get, so integrating both sides, left hand side 0 to t, ddt of e to the power minus at x of t dt, and right hand side 0 to t e to the power minus a tau b u of tau d tau, because tau any time interval t equals to tau. This is the initial time t equals to 0. This is the final time, and tau intermediate any point, and at that time t equals to tau. So 0 to t total integration, and e to the power a tau for this point b into u tau d tau. This is the integration form. Then we get left hand side e to the power minus at x of t 0 to t, and right hand side 0 to t e to the power minus at b u of tau d tau, and left hand side integration, first upper limit e to the power minus at x of t, this is the first value, and second value e to the power minus 0, and e to the power minus 0 means identity matrix, and x of 0 or x of t0, x of 0 I into x of x0, 0 to t, left right hand side same, e to the power minus a tau b u tau d tau. Then we get, just shift I x0 right hand side, and we get, we take e to the power minus at x of t I x0 plus 0 to t e to the power minus a tau b u tau d tau, then multiplying both sides e to the power minus 80, and we get divided by e to the power minus 80, sorry, divide both sides e to the power minus 80, and we get x of t, left hand side x of t, just x of t, and this is cancel out, this is cancel out, and right hand side e to the power 80 into x0 plus e to the power 80 into next term, 0 to t e to the power minus a tau b into u tau d tau. So e to the power 80 into e to the power a tau. Then we get e to the power 80 x0 plus 0 to t e to the power a t minus tau b into u tau d tau. This is the second term. Just this plus this, e to the power a into e to the power a t minus tau b into u tau d tau. This is equation 7. So xt equals to what? Xt equals to this is equation number 7, e to the power a t x0 plus 0 to t e to the power a t minus tau b into u tau d tau, and put phi t equals to e to the power a t. So e to the power a t equals to phi t, because phi t is called state transition matrix, and state transition matrix equivalent to e to the power a t, and then we get e to the power a t minus tau equivalent to phi of t minus tau, just put e to the power a t minus tau and e to the power a t, then we get xt equals to phi t x0 plus 0 to t phi of t minus tau b u tau d tau. This is the very important equation. When the initial time t0 and the final time tf, then the state equation is x of tf, final time tf. So put t equals to tf, phi of tf minus initial time t0, and x of t0 plus t0 to tf, phi of tf minus tau b u tau d tau. Then this is the transition matrix, state transition matrix. Put phi of tf minus t0 equals to e to the power a tf minus tau. So put here e to the power a tf minus tau, tf minus t0 x t0 plus T0 to Tf. This is equivalent to phi of Tf minus tau e to the power a Tf minus tau b u tau d tau, where Tf greater than final time greater than T0 and phi of T equivalent to e to the power at. This is the state transition matrix properties. Then we get, without loss of any generality, we can assume that the desired final state x of Tf equals to 0. This is the important value, and put x of Tf equals to 0 for some finite time Tf greater than T0, given that the initial state x of Tf not equals to 0, then it gives, when left hand side equals to 0, x of Tf equals to 0, this is the equation 0 equals to e to the power a Tf minus T0 x of T0 plus T0 to Tf a e to the power a Tf minus tau b u tau d tau. So e to the power just this term, this side, then e to the power at Tf minus T0 x of T0 minus T0 to Tf e to the power a Tf minus tau b u tau d tau. Then what is the x of T0? X of T0 equals to T0 to Tf e to the power minus a Tf minus T0 e to the power a Tf minus tau b into u tau d tau. Then e to the power a into e to the power b. What is the formula? Just add and we get addition, and we get x of T0 equals to T0 to Tf e to the power a Tf minus tau minus Tf plus tau b into u tau d tau. Tf minus T0 minus Tf minus plus. So Tf minus tau minus Tf plus T0. Then Tf cancel. This cancel, and we get T0 minus tau. So the next equation, x of T0 initial state equals to T0 to Tf e to the power a T0 minus tau b u tau d tau. Then we get x of T0 equals to minus T0 to Tf. This is equivalent to phi of T0 minus tau. By using state transition matrix, phi of T0 minus tau equivalent to e to the power a T0 minus tau and b of u tau d tau. By Cayley-Hamilton theorem, the state transition matrix can be written as, this is the Cayley-Hamilton theorem, phi t equals to e to the power a t, L inverse Si minus a whole inverse, and this is equivalent to k equals to 0 to n minus 1 summation alpha kt into a to the power k. This is the very important formula, phi t equivalent to k equals to 0 to n minus 1 alpha kt a to the power k. Then we get put where alpha akt is the scalar function of t. Then put just the value phi of t0 minus tau, and we get e to the power t0 minus tau k equals to 0 to n minus 1 alpha k t0 minus tau a to the power k, and we put in this equation and get x of t0 equals to what? T0 to tf. Just put here. This is the Cayley-Hamilton theorem, and this is equivalent to ultimate phi of t0 minus tau. Phi of t0 minus tau equivalent to k equals to 0 to n minus 1 alpha k t0 minus tau a to the power k. And x of t0 equals to minus k0, k equals to 0 to n minus 1, just a to the power k into b outside, and within third bracket integration t0 to tf alpha k t0 minus tau u of tau d tau, next term, and then again put gamma k equivalent to t0 to tf alpha k t0 minus tau u tau d tau. Just put here this value equivalent to gamma k, and we get and we get x of t0 equals to this equation. So x of t0 equals 2, then minus this minus and put k equals to 0 to n minus 1, and we get a0, k equals to 0, a0 plus b into gamma 0, a1 plus b into gamma 1, a2, and b into gamma 2 plus dot 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 a cube, b into gamma 3 plus dot 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 a to the power n minus 1 last value, b into gamma n minus 1. This is the xt0 equation, and then we rewrite xt0 equals to what? Just b, a square b, a cube b. From this part, this is the b, this is ab, this is the a square b. Similarly, last term a to the power n minus 1 whole into b, and gamma 0, gamma 1, gamma 2, gamma 3, gamma n minus 1. This is the column matrix multiplying b into gamma 0 and plus ab into gamma 1 plus a square b into gamma 2 plus dot 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 a to the power n minus 1 b into gamma n minus 1. So this is the xt0 equation, and b a b a square b a cube b a to the power 4b dot 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 a to the power n minus 1 whole into b. This is equivalent to q0. This is equivalent to q0, and this is equivalent to gamma. So this matrix equivalent to q0, and this matrix equivalent to gamma. So this is the q0 matrix, and q0 is called controllability matrix. This is also called controllability matrix. So q0 equals to b a square b a cube b a to the power 4b dot 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 a to the power n minus 1 b, or gamma equals to what? Gamma equals to minus q0 to the power minus 1 xt0, and this is equivalent to what? This is the inverse matrix. This is equivalent to adjoint adj, adjoint of q divided by determinant of q0, determinant of u0. So this value not equals to 0, that means non-singular. If this is equals to 0, so gamma undefined, so this is not equals to 0. This is the properties of the systems. So q0 should be non-singular matrix. This is the very important, because q0 inverse equals to adjoint of q0 divided by determinant of q0. q0 non-singular matrix, and q0. Now the controllability matrix may rewrite as follows. Given an initial state x of 0, find the control vector so that the final state x of tf equals to 0 for finite time tf. This means that given x of 0 and controllability matrix q0, solve for control vector, that is gamma equals to minus q0 to the power minus 1 x of 0. This means that q0 should be non-singular, so that inverse of q0 exists, that is the rank of the controllability matrix is n. This is the very important part. q0 matrix controllability, rank of the controllability matrix is n. That is, there exists a set of n linearly independent column vector. A control u of t exists which transfer any given initial state x of 0 to the origin of state space if the vector of gamma equals to gamma 0, gamma 1, gamma 2, gamma 3 dot 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 gamma 4 dot dot gamma n minus 1 whole transpose can be obtained from equation. Kalman test for controllability, it requires that the n cross n matrix where q0 equals to b a b dot 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 a to the power n minus 1 whole into b be non-singular, that is its rank of the equation equal to n. That means this matrix singular, also the rank of this matrix equals to n. So these two conditions if satisfied, then system controllable, otherwise uncontrollable. This result can be extended to the more general case where the input vector is a dimension m in the equation. If dimension m, what is the x dot t equals to xt plus bu of ut, and n cross m matrix, u is an m vector and b is n cross m matrix, then the controllability matrix or controllability condition in this case can be stated as the n cross nm matrix. This is the very important, where Q0 has a rank n. The matrix Q0 is known as controllability matrix. For complete state controllability, there all the column of Q0 must be linearly independent. This test for deciding the controllability is known as Kalman test for controllability. So this sentence again, the matrix Q0 is known as controllability matrix. This is the controllability matrix. For complete state controllability, this is also very important sentence. This is the complete state controllability. Therefore, all the columns of Q0 must be linearly independent. This test for deciding the controllability is known as Kalman test for controllability. Kalman test for controllability. Theorem on controllability. A system is said to be controllable at time t0 if it is possible by means of an unconstrained control vector to transfer the system from any initial state to any other state in a finite interval of time. Controllability depends upon the system matrix A and the control influence matrix B. Already discussed, controllability system depends upon A matrix and B matrix. The main controllability theorems are the state equation 1 or the pair AB is controllable if and only if the controllability matrix QC equals to BA square B dot 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 A cube B A to the power n minus 1 whole into B that has rank n, that is full row rank. The state equation 1 is controllable if the n cross n controllability matrix Q0 is non-singular for any non-zero finite n. Theorem on controllability. If the system has a single input and the state model is in controllable canonical form, then the system is controllable. Another condition, when A has distinct eigenvalues and the Jordan diagonal canonical form, the state model is controllable if and only if all the rows of B are non-zero. And where A has multiple order eigenvalues and in Jordan canonical form, then the state model is controllable if and only if each Jordan block corresponds to one distinct eigenvalue and the element of B that corresponds to last row of each Jordan block are not all zero. So this is the controllability test by Kalman test. Thank you.